Hello, everybody. I will start my another coding practice. So today I will solve this question: count complete tree nodes. Okay. So in this question, I'm given the root of a complete binary tree. Return the number of the nodes in the tree. According to Wikipedia, every level except possibly the last is completely filled in a complete binary tree, and all nodes in the last level are as far left as possible. It can have between 1 and 2 nodes inclusive as the last leverage. Design an algorithm that runs in less than O(n) time complexity. I see. Okay, so yep. In this question, I'm given a complete binary tree, and I will return the number of the nodes in the tree. And yeah, if I just want to count the number of nodes in the tree, I can use the recursion. So for every node, I return the number of nodes which exist, I mean, under the current subtree, under the current node. And yeah, I just have to call that recursion function for the root node, and I will get the number of nodes. However, this approach takes O(n) time because I have to, in the recursive functions, in the recursion, I have to visit each node. Yeah. However, there is a, additional information that the, I mean, given tree is a complete binary tree. Yeah. So I can make use of that information. So again, I will clarify the definition of complete binary tree as far as the left. Except, okay. So I can say the complete binary tree is something like this. So until the last level, there is some node. However, in the last level, maybe there aren't all the nodes in that level. However, the nodes, I mean, should be like this. So in the last level, in the lowest level, um, I mean, at some point, there is a kind of boundary, and until that, in the left, nodes in the same level, there are nodes. Yeah, and yeah, and after, on the right hand side of that boundary, there isn't any node. That's it. So I think where I can, oh, yeah. I think what I can do is that. So my quick idea is that I can know how deep is, how high the height of the tree by just traversing, logN time. Especially by just, I mean, pro, I mean, from the root node, I keep left down all the time, and I can count the height of the tree in logN time. And one more information I'd like to know is where is the boundary in the last level? Hmm. So I somehow would like to know where is the last node in the last level. So probably I can do something like this. So when I start from the root node, and when there is left node and the right node, it means that the boundary is on the left subtree. However, here, if the right node doesn't exist, but the left node exists, then I can say the left child node is the last, boundary. Last node in the last level. Yeah. Let me think a few more examples. Yeah. Let me think of this. In this case, I go here and then here. Oh no, here. Then I go to here. No. So I mean, I'm thinking how I can get the last node in the last level, you know? One possible approach is doing the binary search in this level. No, it doesn't work. Yeah, I just thought I just do the binary search in the last level, but reaching the last level takes logN time, so the total complexity should be logN times logN is n. So it isn't, it doesn't satisfy. Okay, so at least I can say from here in this example, I cannot decide where to go, left or right, to find the last node in the last level. Hmm. So between 1 and 2. Oh, nothing but awesome. Yeah. Okay, so let me think once more. So at least I can say, as I said, I have to go down. I mean, traverse this and this. I see. So okay, maybe I've understood. So as I said, from this node, I cannot say which of left or right sub tree the boundary is. However, yeah, and I think hmm, Okay, wait a minute. So okay, I understood maybe. Oh, mm, wait. So okay, so let's think if there is a node here and here. So how can I find this? I can find it when I go this and this. But it's also possible that the tree doesn't have the child node until here. So in that case, I have to go to the right direction and keep going. So it totally have no idea which should be. And reaching the, you know, bottom level takes logN time. Hmm. Wait, design an algorithm that runs in the overwhelm time complexity. So I don't have to make it log n. I just have to do the traversal. And if, okay, right in this order from root, I'd say 1, 2, 3, 4, 5. Then come back to here and, oh, sorry, I mean, the, I will try to find it in order traversal. And so I first revisit this and 1, 2, 3, 4, 5, 6, 7. So what I can say is when I find that there isn't node in the, okay, so my point is that I will do the recursion traversal so that I should visit the, I mean, lowest node from left to right order. Then at the moment when I find that there isn't a node in the lowest level, I stop the traversal there because my, purpose is already met. I know the height of the tree, and also I know how many numbers of nodes there are in the last level. I don't have to do traversal anymore. So in the worst case, this takes all of time, but in the better case, it is earlier than that. Yeah. Okay. But it's still overwhelmed. I really have no idea how I can do it less than over time. So let me implement with that approach. So as I said, I will guess the height first, and then I will try to then I can calculate it. So if the height is 1, it should be 1. If the height is 2, it should be 1 plus 2. If the height is 3, if the tree is completely filled, it should be 1 plus 2 plus 3. So this is the number of nodes if the tree is completely filled. And from here, I will remove the number of nodes which is missing in the lowest level. So it should be like this. So this is what I should return. Okay, so let me implement this. Yep, so this is it. Okay, now I will implement two methods, get height and get num left nodes. Wait. Okay. So for this is quite simple. I just have to keep going left. Is that it? Oh, by the way, root can be num. Yep. In that case, I will return 0 immediately. Yeah, in this way, the height should be more than 1 and it should, yeah, more than or equal to 1. Yep. Okay. Yep. So I start from the root node and I move the current node pointer. And if current node still has the left node, I move the pointer to the left child and increment the count. Yep. Okay, so now I implement the get number of nodes. So here it takes all of n time. I will do the recursion. So oh, and I want the tree height here. Okay, so I will count the number of leaf nodes with count. Okay, so let me make this in the method. Okay. So what I should do is I increment the count when I find the leaf node, and I do the recursive function visit method, and I start from current level 0. And because the height is this, I can say if current level is equal to height minus 1, this is leaf node. So I append count. Then I finish the recursive function. So this is the base case. And otherwise, and also obviously, if root is none, I have to return. Yeah. I think this shouldn't happen actually, because I visit the nodes from left to right order. So, and my goal is to finish the recursion before traversing all the nodes. So in line 56, I will take a look at root left and root right. And I code the recursive function. Yep. Then, as I said, what I like to do is finish the recursion in the middle if I find that I can't find the leaf node anymore. So what I mean to do is if the current level is height minus 1, and if the root is none, then that's the end. I will return the boolean if we should finish the iteration or not. So and I can say, as long as I finish the iteration in this way, in line 54, I can say if I find the root, is none, definitely is as the, leaf level. Yeah, so I return it in this way. Okay. Then here in line 61, instead of doing this, I will call it twice. And here, if this is returns true, I finish it. Okay, this is it. So let me quickly check. So in line 52, I check if the root is known. And if the root is known, it means that it's the leaf level, and I should return false. And then line 56, if the current level is height minus 1, okay, let me change it in this way. So oh, I have to return true actually. No, I have to return false. Yep. And I don't need it. Okay. I think this is more clear. So if the current level is height -1, in that case, if root is known, I don't increment the count and I return true, which means I should end the recursion. And if root is not known, then I found the reef node, so I increment the count and return false, which means that I need to keep recursion. And then in line 59, I visit the left node, and if it returns true, which means that I should finish the recursion, then I finish with true status. And in line 61, I visit the root right. Yeah. Okay. So for this, actually, it doesn't matter what I return from here. Because left, I mean, when the, recursion result is returned from the right child, at that moment, I do finish all the recursion steps. Yeah. Because it doesn't care. So it doesn't matter. Okay, so this is it. Okay, let me quickly walk through my code with, say, this example. So in this case, firstly in line 34, root is not known. So I go to line 37 and I will guess the height. And I will, in the line 44, get height method. I start from current is root node, which is 1, and age is 1. Then current to the left is 2, which is not known. So current is current to the left, which is node 2. And high age is now 2. And then current to the left is known. So I finish the iteration now, and then I return the age, which is equal to 2. So now I get age is equal to 2. Then I will take a look at n. So for n, I count the leaf nodes. Okay. So in line 42, I call the get num leaf nodes, and I start with count 0. Yep. Okay. Then I visit root node, which is 1, and current level 0. And current level is not height 2 minus 1. So I go to line 66 and I visit root left and current level plus 1. So this means that I visited with 2, 1. Yeah. Then in the code function, in line 59, current level is now 2, which is equal to height minus 1. No, current level is now 1, which is equal to height minus 1 is 2 minus 1 is 1. So I will see if root is known or not. No, if current root is not 2, so this is not known, so I increment the count and I return false. Okay, now count is 1. Then I come back to node 1, 0. So now I call it with non-1. Yeah. Then in line 59, I guess the current driver equal to height minus 1 true, and the root is not true. I return true. So which means that in the Here in line 68, true is returned. Yeah, but wherever it returned here, I finished the iteration. So yeah, okay. Oh, let me say this is null. Wait, this should be true. No, sorry. This actually matters. So if this is true, I should finish true. Oh yeah. Okay. Because obviously, in the case when I have the tree in this way, yeah. In this case, this returns true or false here, and in this node, I have to make the decision I should continue the recursion or not. So yeah, the result from the right chart also matters obviously. Okay, so so I'm pretty sure on my code, even though there are some cases that I couldn't cover, like what happens if the should end is returned with false, then I should stop the, recursion. I couldn't cover that. But even that being said, I covered all the code lines in this, method. So let me execute my code. Oh, sorry, this. And I should make count non-local. Okay, so something is going wrong. Oh, obviously my mistake was num complete, I think. No, let me print it out. Okay, so I get 3, 3. This is true. Num complete is now 6. This isn't true. Wait. So I think my first mistake is this should be h minus 1. So as the level h, I mean, maximum level in this tree should be h minus 1 because it's 0 index. So that's why I have to take care. Also here, num complete is wrong. So it should be 7, but it's not 6. So this should be not this, but 2 to the power of 8 minus 1. Because the number of nodes in each level is 1, then 2, then 4, and 8. So when I take the sum of them, I find that it should be 2 to the power of h minus 1. Good, accepted. Okay, so now I will submit my code. Good, it accepted. Okay, so let me quickly wrap up on today's practice. So today's question is count completely 3 nodes. And, oh, sorry. I forgot to do the complex analysis. For time complexity, it should be, in the worst case, O of n. But hopefully it's smaller than that because I stopped the recursion immediately after I find the last leaf node. And for space complexity, it should be O of log n. because, yeah, of the recursion stack. So the number of recursions would be logN, which is the height of the tree. And aside from that, I don't use any, data structure, which takes more than constant time complexity. Okay. So I wrap up into the question. So today's question was count complete tree nodes. So I'm given the completely binary tree and I return the number of nodes. So yeah, I use the recursion based query. But one thing I had to take, no, I actually didn't use the recursion for the usual way. So, to get the, to count the number, firstly, I guess the height of the tree. And also I find out how many leaf nodes there are in this tree. In this process, I use the recursion, but I made sure that the recursion is terminated immediately after I find the last leaf node. Yep. So, and from the height and number of leaf nodes, I calculate the total number of nodes in the tree and I return it. Okay, thank you so much.